Hello everyone, welcome to the session. So in this particular video, we will talk about the sorting algorithms. So let's discuss about that. So these algorithms, whatsoever we are discussing here, that also we will apply on top of an array-based data structure that we have already covered up. Let's get started. So first of all, whenever someone is telling you that sorting algorithm, so what does that mean? What is the meaning of a sorting algorithm? Sorting algorithm. The simple meaning is that given a set of elements which are stored in any data structure, for example, as of now we are talking about an array. So suppose I am having some set of elements. For example, here I am having 20, 10, 12, 17, 27, 42, 39. Suppose these are the elements that we have, which are stored in an array. Now here we are having the index numbers also, right? It will start from 0, then we'll move ahead 1, 2, 3, 4, 5 and 6. So here in total I am having 7 number of elements, correct? When I am applying any sorting algorithm, so whenever we are applying any sort of a sorting algorithm, so what we are trying to do here is that, just try to understand here. Suppose you have applied any sorting algorithm. So let me tell you, there are so many sorting algorithms that we have, but there will be a broader classification of that we will discuss here. So when you apply any kind of sorting algorithm, the expectation will be that you will give an array either in ascending order or in descending order. Means either in increasing fashion or in decreasing fashion. For example, the expectation will be that your array should look like 10, then 12, then 17, then followed by 20, then 27, then 39, and then 42. So this is a kind of an array which is expected from you or from your code. So this is the indexes that we got as a final output for each and every element that we have. This is the meaning of sorting. So this is something which we called as a sorted array. This is something which we called as a sorted array. So here basically what we are trying to do is that we are expecting that given any kind of array that we have, once I will apply any kind of a sorting algorithm out of so many sorting algorithms that we will discuss in our course, the expectation will be that the array should look like this manner. Now, how many different kinds of sorting algorithms we have? As I told you that we are having a variety of sorting algorithms, and we will understand that at what point of time or at what scenario which particular sorting algorithm we should go for. But before understanding that point, let me try to give you a very simple example. If suppose someone is asking to you that how many different kinds of sorting algorithm do you know? Students generally say, or they generally start with, I know bubble sort, insertion sort, selection sort, merge sort, quick sort, count sort, radix sort, bucket. No, this is not the correct way to answer this question. Your answer should be that broadly classified, the sorting algorithms is divided into two parts. So any of the sorting algorithm, whichever you came across, is broadly classified into two parts. One is something which we called as a comparison based sorting algorithm. Comparison based. Okay. Another one is something which we called as non-comparison based sorting algorithm. Non-comparison based sorting algorithm. Now what does that mean? When I'm saying that comparison based sorting algorithm, the simple meaning is that here the array elements that you have, they are doing some sort of comparison. So comparison goes on within the values that we have inside the array. As the name suggests itself, comparison based. So when we talked about comparison based sorting algorithms, we will see that inside those algorithms, there is always a comparison within the values that we have. But when we talk about non-comparison based sorting algorithm, you will observe that Internally, values are not comparing. It's just the internal structure, the characters or the words that we have or the numbers that we have. We are doing some other thing apart from the direct comparison within the values. So in a broader sense, we are having two different kinds of sorting algorithms. One is called as comparison based. Another one is called as non-comparison based. When we talk about comparison based, so here comes that there is a comparison within the values in an array that we have. For example, we have maximum sorting algorithms under this category. So the very basic is selection, sort, the bubble sort that we have. Every sorting algorithm, whatever I am writing here, we will discuss in our course. Selection, bubble, afterwards you should know about insertion sort. After that, you should know about quick sort. Okay. After that, there is a merge sort. Afterwards, you have heap sort. So these sorting algorithms are the algorithms which came under the category of a comparison based. It means that whenever I am using these algorithms, you will observe that somehow I am comparing the values, the numbers that we have inside the array with each other. And then I am doing a sorting algorithm. Obviously, the final output will be same for every sorting algorithm that you will apply. Now the question which should come in your head is that if we can do this thing with one algorithm, for example, using selection sort only, we will be able to get a sorted array, then why there is a need of so many sorting algorithms? You will easily able to get that once you will be able to get an idea of all these sorting algorithms. Because what you need to understand in step by step when I will talk about these sorting algorithms, first of all, you need to understand the approach of every sorting algorithm. Okay. You just need to focus on the approach on the very first thing. Secondly, you need to understand that on what scenarios mainly, which sorting algorithm will be the optimized one. How you will get the optimized one? How will you compare that whether this sorting algorithm is optimized or not? By using the concept of, everyone I hope now knows, time complexity and the space complexity. By using the concept of time complexity and the space complexity that we have. So here, these two things we should know pretty well. For each and every sorting algorithm, whenever I will write the code, I will try to discuss about these specifically time and space complexity. And then we will also discuss that at what point of time means that at what scenario we should go for what kind of algorithm, right? Apart from that, then you have a non-comparison based sorting algorithms as well, where there is no as such comparison of the numbers or the values that we have inside the array. In this, it includes maybe the count sort that you have. This includes the radix sort that we have. This includes the bucket sort that we have. So here basically we are having mainly these three different kinds of sorting algorithms which came under this category of non-comparison based sorting algorithm. Here if you will talk about this quick sort and this merge sort, these two came under the applications of divide and conquer. These two came under the applications of divide and conquer module. So when I will talk about this module, at that point of time only, we will try to discuss these two quick and merge sort. But apart from that, everything we will try to discuss in our array based data structure only, because I want to show you that with the help of that data structure, what things we can do. Then only I think you will be able to appreciate that data structure pretty well, right? So that is the overall idea behind the sorting algorithms that I want to give you with the help of this video. So in this video, in a nutshell, we have understood that in a broader sense, we have two different types of sorting algorithms. One is called as comparison based, other one is known as non-comparison based. We have seen what is the major difference between these two things, right? And then we have seen which sorting algorithms comes under the category of this comparison based and what sorting algorithms will come under the category of non-comparison based. Afterwards, I have also talked about that what things you have to keep in your mind while moving towards the next videos, where we will talk about the different kinds of sorting algorithms that we have. One thing you need to see that how one sorting algorithm is different from another one via approach, logically how it is different. Secondly, you have to see that in what scenario it will be beneficial for us to use that kind of sorting algorithm or the another one. On the basis of what? On the basis of simply time and space complexity. Then only you will be able to see that which one is more optimized sorting algorithm that we have, right? So before moving towards the concepts of the different kinds of sorting algorithms that we have, whether it be comparison one or it will be non-comparison one, I just want to talk about few basic terms that usually you will encounter whenever I'm talking about any of the sorting algorithm. And even in interviews also, you can face these questions because many students are not aware about these key terms which I am talking about here. So please pay attention towards this session as well. So the first important term where this session will be completely based on is about the difference between stable sorting algorithm and unstable sorting algorithm. So what I am saying is that what is the difference between something which we called as a stable sorting algorithm versus unstable sorting algorithm. Okay, so this is the first thing that we need to take care of. Stable versus unstable. Yes, sorting algorithms are also stable and unstable, right? So just try to understand that what is the meaning of stability in terms of a sorting algorithm that we have. So when we talk about stability, the simple meaning is that whenever they are sorted, means after applying the sorting algorithm on top of any of the unsorted array, their relative order should be maintained. So whenever I am talking about stable meaning in terms of the sorting algorithms that we have is that their relative order should be maintained after applying sorting algorithms. After applying sorting algorithms. This is the important thing. Relative order should be maintained. What is the meaning of this line? I just want to convey to you. Don't worry if you will not able to understand this line as of now. Let me try to give you one example. With this, everything will be clear. For example, what we can do is that we can take some dictionary. Now, what is dictionary? I hope everyone knows. Dictionary is a data structure in Python which is completely based on the concept of key value pairs. And this internally is using a hashing data structure that we will talk about in our upcoming course as well. You will get in detail explanation of hashing data structure. So what will happen is that in this particular data structure, there will be a mapping of key value pairs. So consider that we are having a dictionary which contains maybe 4, 2, which contains maybe 5, 7, which contains maybe 4, 3. Then there will be a data like 6, 8. Then there will be a data like maybe 7, 10. For example, this kind of data is given to you. Okay. Now, suppose I am saying that I want you to sort this particular dictionary on the basis of the keys that you have. So you will apply one sorting algorithm. You will apply one sorting algorithm. And what that sorting algorithm is doing is that sorting algorithm will try to sort your data on the basis of the keys. This is the key, for example. So on the basis of this key, your sorting algorithm is able to generate a data in a increasing fashion. So basically, you are getting 4,2. Suppose afterwards, by default, no. So you are getting 4,3 also. Afterwards, you are getting 5,7. I thought by default it is in a sorted fashion, but it's not like that. So 5,7, then you are getting 6,8, and then you are getting 7,10. This is the result that you are getting. Okay. Okay. So is this fine? You are saying that actually it is fine, because if you will see the keys, you are getting in a sorted fashion. Okay. Now I will ask from you, is this fine? 4,3, 4,2, then 5,7, then 6,8, then 7,10. Is this fine? You will say to me, yes, Priya, this is also fine, because here also we are getting in a sorted fashion. Now, there are few algorithms which will generate the first answer. Then there are a few algorithms which generate the second answer to you. The question is that which one is the stable one and which one is the unstable one. Here if you will see, now I am coming to the point, please pay attention towards this part. If you will see, 4,2 is coming first. Afterwards, this 4,3 pair is coming up. So by saying the relative order, it means that as your final output, 4,2 should come first, and afterwards 4,3 should come. And then there will be a sorted fashion. The way you are getting is correct. Or in other words, so if this is happening, this is something which we called as a stable sorting. This is something which we called as a stable sort. So if any sorting algorithm is giving you this kind of result, you will categorize it as a stable sort, because here the relative order is maintained. Here whichever pair is coming up first is getting the output as a first only, right? That is the thing. Now next important point. Suppose the order is not maintained. Suppose the relative order is not maintained. At that point of time, that particular sorting algorithm is categorized as not a stable sorting algorithm. Very important point to understand. So one thing we just understood is that whenever we are talking about stable one, it means that the simple point here to understand is that relative order will be maintained. By saying relative order, I hope now everyone will be able to get a clarity that whichever value is coming up first will come up first as an output. For example, even you are having some single values. For example, you are having 4, then 5, then 7, then suppose you are having 3, then you are having again 4, again you are having the data as maybe 6, then you are having suppose 10. So when you are applying a sorting algorithm on this particular array, so suppose this is 4 and this is 4, but this 4 you can, if in order to differentiate this, suppose I am writing it as 4a and 4b. So either you are getting this as a result 4a then 4b, right? Sorry, 3 will come ahead after sorting. So 3, then maybe 4a, then maybe 4b, then you are getting 5, 6, 7 and 10. Or you can also get from some other sorting algorithms as this kind of output: 3, 4b, 4a, 5, 6, 7 and 10. You can get either the first one or the second one as a desired output. Now the question is that which particular output is the stable one. Now I hope everyone is able to give me the justification and the answer for that. That relative order should be maintained. One thing you have to keep in your head. 4A is coming first. So in your final sorted output, 4A should be the leading one as comparable to 4B. So this one you can say is a stable sort. And this one you will say, because here relative order is not maintained, as the unstable sort. That is the only difference. Majorly, you will see, we will discuss in the future classes about the quick sort, as well as we will also talk about the selection sort and the heap sort. These three, at least you should know, are the ones which are unstable sorting algorithms, means they will not able to retain the relative order. So in an interview, this question can be asked from many students, and it can be asked from you as well, that first of all, do you know the difference between a stable sort and unstable sort? So I hope now everyone will be able to tell the proper answer and justification for that. And then they can ask from you, because in stable sort, there are so many sorting algorithms. Even apart from this, maximum all are lying in this particular category only, stable sort. So they will specifically ask from you that, do you know what are the sorting algorithms which lie under the category of this unstable sort? So these three things should be in your head, that quick sort, selection sort, and the heap sort will be the one. Why is that so? What's the justification for that? Once you're able to understand the algorithm of these three sorting algorithms, then I will give you the justification also for the same. But as of now, you just need to keep in your head, because once I will go to the explanation towards any of the sorting algorithm, I'll directly say that it's a stable sort or it's an unstable sort. At that point of time, I don't want any student to be confused like what she is saying. I don't even know what is stable and unstable. That's why I'm putting all these videos prior, so that you will be able to know end to end everything once we will move towards the concepts for the same. There are two words that you will listen quite a lot whenever we are talking about sorting algorithms. One is in place and another one is outplace sorting algorithm. Okay, in place and outplace sorting algorithm. So what does that mean? What is the meaning of in place and outplace sorting algorithm? So whenever we are talking about in place sorting algorithm, it simply means that we are not using any kind of extra space in order to sort an array. So as the name is also suggesting, that here we are not using any extra space. So that is the important point here to understand, that here we are not using any extra space, okay, to sort an array. So when you are not using any extra space to sort an array, that is something which we are talking as a in-place sorting algorithm. But suppose if you are using any extra space, for example, you will came across many sorting algorithms that we will cover up in our upcoming classes, where you will see that one thing is that we are having the array. That's fine. That's not an extra space. But apart from that, in order to sort that array, I need some extra space. In order to run that code, we are using or we are creating some extra array, right? At that point of time, so outplace says outplace, as the name suggests. Outplace means that you are using an extra space. You are using an extra space to sort the array, right? This is the meaning of outplace sorting algorithm. That is the major difference. For example, we will come across one of the very famous sorting algorithm, and this is the one which is widely used in maximum scenarios because it is the most optimized one in terms of the time complexity, although it will use some extra space. So it is called as merge sort, that we will discuss about in our future sessions. As I told you, it's an application of divide and conquer. So in that module, you will see a complete in-depth explanation of this merge sort. Okay, so we will discuss about this application inside the application of divide and conquer module. But as of now, I just want to let you know that what is the difference between these two, and which one is the famous among them, which is specifically known as a outplace sorting algorithm. Okay, so I hope that I'm making sense to everyone. If someone is asking to you now in any of the interview that what is the difference between in place and outplace, or what is the difference between stable and unstable, I hope you will be able to answer it very much clearly. Here, if you will see on the blackboard, I have taken some random set of data elements that I have in my array. Okay. Now, as you can see that these are not in a sorted fashion. Our target is to reach to a point where we want our array in a increasing order. Okay. So by default, index will start from 0, that we already are aware of all these facts. So 0, 1, 2, then 3, then 4, then 5, and then 6. So here, this is the array elements that we have. Okay, so we are having in total 7 number of elements. Right. Now, how basically this bubble sort will work? Try to understand the approach behind that. Okay, that's the only thing that you have to take from this session. Okay, so basically what is happening is that it will try to compare the consecutive 2 elements, and if suppose the upfront element means the one element is higher as comparable to the next one. For example, in this particular case, if you will see 70 is greater than 20, right? So what it will try to do is that it will try to do the swap. So basically what will happen is that in the first pass, in the pass number 1, when you have the original array, what will happen is that the 2 elements will start comparing with each other. So 70 and 20 will do the comparison, and as 70 is greater than 20, so there will be a swap. So what will happen is that 20 will come here and 70 will come here, right? Now the 70 and the 50 will do the comparison, and here, because again the value of 70 is greater than 50, we have to make it sorted in a increasing fashion. It means that we should have the greater element towards the right extreme, but it's not so. So again there will be a swap. So 50 will come here and 70 will come here. Now again 70 and 30 there will be a comparison. 30 will come here and 70 will come here. Again 70 and 90 there will be a comparison, and now it is fine. Why? Because 70 is somehow lesser than 90, so it is fine. There will be no swap which is required in this part. Now in the next iteration 90 and 5 will get compared up, and here you can see again there will be a swap which is required because the value 90 is greater than 5. Again 90 and 15 will get compared up, and here again 90 value is somehow greater than 15. So here 15 will come here and 90 will come here. So in the very first pass number 1, how your array will look like? It will be 20 followed by 50 followed by 30 followed by 70 followed by 5 followed by 15 followed by 90. So here you are having a set of elements 0, 1, 2, 3, 4, 5 and 6. So here we are having 7 elements in this kind of fashion, where if you will see, try to observe here, this element will be actually at its own location. 90 after fully sorting of this array also will be located at 6th index, because this is the highest element that we have inside our array. So what will happen is that in the next iteration, what I will do is that I will try to get rid of that last element in the first pass, and I'll just do the same thing for the remaining elements. Now what will happen? Again the same thing you have to do. 20 and 50 will get compared up. These are fine because 20 value is less than 50. We will move ahead. 50 and 30. Again there will be a swap which is required because 50 is greater than 30. Again 50 and 70 is fine. 70 and 5, swap will be required. 70 and 15, again swap will be required. So after pass number 2, what kind of array you will be able to get? You will get the value as 20, followed by 30, followed by 50, followed by 5, followed by 15, followed by 70, followed by 90. So here if you will try to see, you are having these elements where again if I will write the index number 0, 1, 2, 3, 4, 5 and 6. Here again if you will see, in the second pass, the last second element will be its own position. Means even I will complete my sorting of these complete remaining elements as well. 70 will remain its own actual position, means at index 5. It means that what you are observing that at each and every iteration, for example, the first iteration, one element is sorted. Second iteration, last two elements are actually sorted. Now what will happen is that in the next iteration, you will only work for these many elements. Again, let me try to work for this. 20 and 30, already fine. 30 and 50, already fine. 50 and 5, no, because 50 is somehow greater than 5. So I need to do swap here. 5 will be here, 50 will be here. Again 50 and 15, there should be a swap which is required because 50 is greater than 15. So 15 will come here and 50 will come here. So after pass number 3, in pass number 3 what you will get? You will get the value as 20, followed by 30, followed by 5, followed by 15, followed by 50, followed by 70, followed by 90. So this is a set of elements that you will be able to get. Again, let me try to write the index number 0, 1, 2, 3, 4, 5 and 6. Here again if you will see, at pass number 3, last third element is its own position. Means what I want to convey here is that in bubble sort, at each and every pass, the next higher element will be located at the extreme end. At first pass, the largest element will be at the last index. In the second pass, you will get the second largest element at its last second index. In the third pass, you will get a third largest element at its last third index, and so on. Now, the same thing you need to do for the remaining elements. That is from 20 to 15. Now, again what will happen? 20, 30 is fine. 30 and 5, not fine because 30 is greater than 5. So 5 and 30 will get swapped with each other. 30 and 15 is also not fine. So again a swap will be required. Now again what array you will be able to get at pass number 4? You will be able to get an array which is 20, which is 5. Let me erase the brackets first. So it is 20, it is 5, it is 15, right? It is 30, it is 50, it is 70, it is 90. Again, let me write the index number. It is 0, 1, 2, 3, 4, 5 and 6. And as you can see, the last 4 elements at pass number 4 will be its own position. Now we need to take care of the remaining elements. At the starting 3 elements are only there. So now what you can do is that again you will look for 20 and 5. A swap will be required. So 5 will be here and 20 will be here. Again 20 and 15. Swap will be required. 15 will be here and 20 will be here. Right? So at pass number 5, what you will be able to get is, you will be able to get the value as 5 followed by 15. So let me erase this brackets here again. 5, 15, 20, 30, 50, 70 and 90. Again, if I will write the index number, it will be 0, 1, 2, 3, 4, 5 and 6. Here if you will try to see, again the last 5 elements are in their sorted fashion. So now we need to look for only the first 2 elements that we have, and if you will observe, these 2 elements are already in a correct sequence. There is no need to do the swap. So after pass number 6, finally you will be able to get a sorted array. Actually at pass number 5 itself it's sorted, but anyhow when we do the comparison, our system will get to know that it's already in a sorted fashion, and it will print this as a final output. So this is the final sorted array that you can see is there. 5, 15, 20, 30, 50, 70 and 90. And yes, it's sorted, it's in an increasing fashion, whatever we want is there. Here if you will see, what we have observed is that the very first point here we have observed that, so here what I can write is that points to note. Now there are few important points that we observe from this approach. What are those important points? The very first point here to understand is that here if you will observe that when we are having the number of elements as 7, so in worst case scenario we will go until the pass number 6. What does that indicate? That if you have n number of elements, in worst case scenario, how many number of iterations or how many number of pass you need to do in the bubble sort? It will be n minus 1 number of passes which are required. The second important point here to understand is that if suppose someone is asking to you that in bubble sort, in worst case scenario, how many number of comparisons are required? Here please note that I am always talking about worst case scenario, because as I already talked about this in the analysis portion as well, that in all the upcoming sessions, our major focus is to optimize the worst case scenario. If we will be able to optimize that worst case scenario, automatically other scenarios will be covered up, right? If a person will be able to optimize, or if a person will be able to handle the worst situation in his or her life, automatically he will be able to handle the average and the best situation in his or her life. That's the same rule which I am applying here. So in worst case scenario, suppose someone is talking to you and saying to you that can you tell me how many number of comparisons are required? In worst case scenario, how many number of comparisons are required? You need to find out the number of comparisons. So here if you will try to observe, at each and every time, what we are saying is that, suppose here we are having n elements. So at first pass, we get rid of n, we are having n minus 1 elements to compare now. As I already told you that the last element is already at its own location. And then we try to compare with n minus 1 elements. Here we are comparing with n minus 2 elements. Here we are trying to compare with n minus 3 elements. Here until so on, we are only left with a single element. Only single comparison at the very end. What I want to say here is that you are starting from n minus 1, then n minus 2 comparisons left, n minus 3 comparisons left. At the very end, it will be like 3 plus 2 plus 1. What is this? When we talked about the simple sum of n natural numbers, when we talked about the sum of n natural numbers, what is that? I hope everyone knows this thing. I'm not expecting anyone to not know this apart. This will be n into n plus 1 divided by 2, right? Now, what is this thing? This is nothing but n minus 1 natural, sum of n minus 1 natural numbers. So instead of placing n here, you need to just place the value as n minus 1. So it will be n minus 1 into n minus 1 plus 1 divided by 2. Or can I write it as n into n minus 1 divided by 2. So in worst case scenario, what's the higher exponential term that we have? It will be n square. So can I say that in worst case scenario, in big O, it will be big O of n square. So the number of comparisons complexity will be coming out to be order of n square. Third important point where we are looking for is the number of swaps that we are doing here. Because in bubble sort, the majorly what we are doing is that we are doing only two tasks. One is the swapping, another one is the comparison. These two are the key important things which we are doing in a bubble sort. So let's talk about the swaps. Here also, if I'll talk about the best case scenario, how many swaps are required? In best case, there will be no swap required. It might be the case that the array is in a sorted fashion or is in an increasing fashion, and somehow you are not requiring any kind of a swap. So I can say that at that point of time, it means in a best case, you might need only, I would say, 0 swaps, right? Only 0 swaps are required. But what will be the worst case scenario? Worst case scenario will be exactly the same, which is equal to the number of comparisons required. It means initially I am having n-1 comparisons, and I am doing n-1 swaps, then n-2, n-3 until 1. Again, we will be able to form up the same series, which is equals to n into n-1 by 2, right? That the number of comparisons equals to the number of swaps in worst case scenario. It means, again, while talking about the swaps, it will be equals to order of n square. So directly, without looking into the coding part, only just theoretical understanding only, with the help of this only you will be able to get an idea that what should be the overall time complexity of the bubble sort. Here if you will see, bubble sort is basically doing two heavy operations. One is something which is comparison, and after doing the comparison, it is looking that whether a swap is required or not. If I will talk about the bigger time complexity of comparisons, it will be order of n square. For swap also it will be O of n square. It means anyhow this bubble sort will be done in order of n square time complexity. Another way to determine the same thing is with the help of writing the code. Means while doing the implementation for the same concept that we have just studied in this session. And that I will show you in my next video. So what we will do in our next class, we will try to see the implementation. In that implementation, straightforward, if you will look for the loops, how many loops are working internally to do the implementation for the bubble sort, you will be clearly able to get an idea. There is not even a need for me to explain you about the time complexity part after I will be able to write the code. But before that, make sure that, because you already know the logic behind bubble sort now, right? You just need to apply two for loops. One is I, which will take care, this is I, which will take care of the first element, because we are always comparing the two elements. First one, and j will be the next element of I, which is I plus 1. So you can try to write the code or the implementation for the bubble sort. I am expecting that if you already aware about the Python programming language, and if you already understood the complete approach about the bubble sort, it will be very easy for you to write the code. And again, once you will be able to write the code, you can take the same array which I have taken here. Even I will take the same array in my implementation class, and your output should be this only, the way we are getting this output. Here, once you will be able to write the implementation, automatically you will be able to understand the time complexity part, which is coming out to be order of n square, because you will observe that you are applying two for loops there, right? So try to do it on your own, because the more you practice the coding part, the more you will be able to get the confidence and more skilled you are in DSA. That is the only mantra I would say in order to be best in this domain particularly. So that is the overall idea behind the bubble sort. I think I have given you all a complete picture where we have talked about the complete overall analysis of this bubble sort. Are we using any extra space here in order to implement the same? Are we using this? No. I am doing all the operations internally in the same array. That's why here if you will see, when we talked about the space complexity, here we are talking about the time complexity. If I will talk about the space complexity part, so as such we are not using any kind of extra space. That's why the same space complexity will be equals to order of 1, means we are using a constant space as such. Afterwards, it's a in-place sorting algorithm, in other words I can say, right? And is it a comparison based or non-comparison based? Obviously, here we are trying to compare the elements within an array, right? I am comparing 70-20, then I am doing a swap. Then I am comparing maybe 70-50, again I am doing a swap. So what I am doing is that I am trying to compare all the elements within an array. That's why it is coming under a category of a comparison based sorting algorithm. That you all know. What does that mean? I have already explained, but it's just for the demonstration purpose, because now you know the approach behind this bubble sort. I have already explained the complete approach. That's why I am relating all those points which we have covered up in our previous videos. So far, I hope that you already have watched my previous video where I have talked about the complete pseudocode as well as the understanding behind the bubble sort. We have seen that how internally bubble sort will work in order to sort the complete array, right? And we have seen that in worst case scenarios, how many number of comparisons are required, what's the time complexity for that. Similarly, for the worst case scenario, how many number of swaps are required. And according to that, we have illustrated that what is the overall time complexity for the same, right? Now, in this particular video, we will talk about the implementation for the same. So now in this video, I will not go towards the pass number 1 until the pass number 6, just like the way I did before. I will directly start doing the implementation, considering that thing in mind that you already have watched the previous video, okay? Now, if you remember, we already have discussed that when we are talking about each and every pass, what is happening? At each and every pass, the last element will keep on removing, because the last element will be having the highest value, and that is already in its own proper location, right? For example, this is the array which we took in the last session, and what will happen is that I will just show you the first pass. So what is happening in pass number 1? 70 will be compared with 20 because the element present at 70 is greater than 20. So we are doing a swap. So 20 will go here, 70 will go here. Again 70 and 50, 70 value is greater, so 70 will go here and 50 will go here. Again 70 and 30, 70 will go here and 30 will go here. 70 and 90, it's completely fine. 90 and 5, 90 will go here, 5 will go here. 90 and 15, 90 will go here and 15 will go here. Meaning, when we talked about the pass number 1, we said that the elements that we will be able to get will be 20 followed by 50, followed by 30, followed by 70, followed by 5, followed by 15, followed by 90. So here if you will see, this particular element, if you will see at the very last position, is actually has its own position. Means even after doing the complete sorting, this particular location will remain as it is. After second pass, you will see that the topmost two highest elements will be at its own proper positions, apart from the remaining elements that we have. So what I can do is that I will try to make one for loop which will iterate from 0 to n minus 1. Inside that, when we are making a comparison, at every pass what we can do is that we can say it will do n minus I minus 1, where the I value will start from 0. So at the very first pass, I want my element to start from 0 and will reach until 6. In the next pass, when the value of I will become 1, what I want is that the element will iterate from 0 to n minus 2. Why is that so? Why is that so? Because I know when I'm saying n minus 2, I'm having how many number of elements? I'm having 7 elements, 7 minus 2 is 5. So that is what I want. I want that my element should traverse from 0 to 5 in the next pass, because the element which is at its 6th position will be always is at its own location even after sorting. So why to take that particular value again and again? That is where you need to do the optimization, and that is where maximum students will not be able to get the point when they're doing the implementation. So let me try to show you whatsoever I have explained here. So what we can do is that we will try to take the same array. So let me try to write down the driver code first. So here what we can do is that I can take the array. This array will contain the elements like 70, followed by 20, followed by 30, followed by 70, followed by, we are having 70, 20, 50, 30. 70, 20, here I read something wrong, 50, 30, after that we are having 95 and 15. 95 and 15. So intentionally I picked up the same array. Now what we can do is that we can store the result in one variable named as result, and we can call our function. So we can give the function name as bubble sort here, which will take the array here, and then what we can do is that we can print the result. So array after applying bubble sort, you can mention like this, okay, and then what we can do is that we can print the result. Okay, now what we can do, we need to define the method definition. So here comes the method definition. Now here what we can do is that, what is the function name? Function name is bubble sort, which is taking the array. Now what we can do is that we can simply try to take the number of elements that we have inside the array. So that we will be able to get by saying length of array. I hope it is making sense to everyone. So once now you will be able to extract that how many number of elements you have inside your array, what you can do is that you can make one for loop which will start from 0 and will go until n. So automatically it will go until n minus 1, start from 0. So here I will say for j in range, and here I will mention n minus I minus 1. That is the point which I want to explain to you at that point of time, that at each and every iteration what is happening is that we are trying to get rid of the last elements that we have. So pass number 1, one element. Pass number 2, the last 2 elements. Pass number 3, the last 3 elements are already in a sorted fashion. So in a nutshell, you can observe that whenever you are applying a bubble sort, you will be able to get the highest elements in the extreme right side. And that is true as well, because when we are doing a sorting, we always want that the highest element will be at the right side and the lowest element will be at the extreme left side, and that is what is happening here. But the kind of approach that we are applying here in case of a bubble sort illustrates this thing pretty well, and I have showed you in the previous session at each and every pass how this is true. Okay, if you are not able to get an idea, please do refer the previous video again, where I have completely shown you that at each and every pass how the elements are getting rid of. At pass 1, last element, pass 2, last 2 elements, pass 3, last 3 elements, and so on. Now we can make simple comparison. If the value of the array of j is greater than the value of array of j plus 1, what we can say is that, so obviously this value will start from 0 and will go until this point. What we can say, if this is happening, I want to do the swap of the elements. So what you can do is that simple swapping we can do by saying add j plus 1, which is equals to add j plus 1 followed by add j. Fine. Now what we can do is that we can simply, once we will be out of the for loop, we can simply return the array. Right? Let's try to see if there is some error we are getting. We will try to resolve it at that point of time itself. We'll see. So let me restart the kernel. Let me just copy this code and let me reopen this thing. New Python 3. If I will copy this. So here you can see that the code which we have written just few minutes back, is showing us the correct result. So it's very simple. The simple point here to understand is that what we are trying to do is that we are trying to make two for loops. One is simply responsible to take each and every element step by step. Inside that for loop, we are taking the element from 0 to n minus I minus 1. Specifically this point you should be able to understand that why is this n minus I minus 1, and I hope I'm making sense to everyone. Here if you will see, we are using two for loops to do the comparison and to get a final output. And that's why the time complexity required to run this bubble sort, as you can clearly say, will be equals to order of n square. So time complexity will be equals to order of n square. Until so far, I hope that everyone is already aware about how bubble sort will work and what is actually the meaning of a sorting algorithm, right? So let's get started. Let me first of all write the term called as selection sort. So now today we will see that what is the logic behind the selection sort and how it is different from the bubble sort that we have understood. So in order to understand the logic behind the selection sort, what I will try to do is that I will try to take some random array, okay, which contains a list of numbers. So what I will do is that consider that we have an array which contains some list of numbers. For example, I'm having 50, I'm having 38, I'm having 45, then we have maybe 79, then we have 19, then we have 27, then we have 29. I think that is fine. Suppose this is an array elements that we have. Now we all know that whenever we are having an array, by default the array index will start from 0. So our array index will start from 0. So 0, 1, 2, 3, 4, 5 and 6. Fine. Now what we will try to do, if you remember in bubble sort, what we will try to do is that we will try to just compare the two consecutive elements, and if the first element is greater than the second element, we will try to do the swap. And in this way, in worst case scenario, for one pass we are doing n minus 1 number of swaps, then n minus 2, n minus 3, n minus 4 until we left with only single element. That's why we have understood that in bubble sort, the worst case scenario, number of swaps requirement will be big O of n square. But now in this particular case, when we are talking about selection sort, it did something smarter. How? It says that why to swap again and again? Why not to take one variable, for example, min, which is basically responsible to take a index of a minimum element. So by default, initially the value of the min will start from 0. Now what will happen is that you will try to iterate in the first pass each and every element. If you will be able to get the element index value which is lesser than the given index value, then you have to update that min value. Meaning what I am saying is that, so by default the value of min will start from 0. Now you will go ahead. 38 is there in the first index. 38 value is lesser than the value present at r of min, which is 50. Yes. So what I will do is that, or what you are saying to your code, update the min value to 1. Now again you will move ahead. If you will see in the next part, 45 is somehow greater, no need to update. 79 bigger, no need to update. 19 smaller than the value which is present at r of min, which is 38. So again you will update the value as 4. So this min variable is responsible to contain the index of the minimum value. Index of the minimum value. This is the purpose of this min variable. Index of the minimum value. Now again it will move ahead. Again it is 27 whose value is not lesser than 19. Then 29 not lesser than 19. Means in the pass number 1, we will be having the value of the min as 4. So now what we can do as a final step is that we are saying that just swap the value of the array of 0, which is the starting value, with the value of the array of min. So what we are trying to do is that, what is the value of array of min? 4. So what we are trying to do is that we will just swap 50 with this and 19 with this. So what we will be able to get after the first pass iteration, we will be able to get the array elements as 19, followed by 38, followed by 45, followed by 79, followed by 50, followed by 27, followed by 29. So this is the values that you will be able to get once you will be able to done with the pass number 1. Fine. Now again here, if you will try to see, this is the array in which, if you will observe, at the very first pass, you will be able to get the first element as the sorted one, which is always at its own location. So in a selection sort, after every pass, you will be able to get the smaller elements. Here you will be able to get the first smallest element. Now there is no need to take this 19 in the next pass. What you can do is that now you're only focused towards this only. You need to basically focus from 38 to 29 because 19 is already a sorted one. 19 is already at its own location. So now what you can do at pass number 2, you can say that the minimum value is equals to 1. Again, by default it is the first element. But now what you need to do is that you need to see that if there is some element which is less than 38 or not. You will keep on iterating 2, no, 3, no, 4, no, 5, yes. So 27 value is less than 38. So you can just replace this value of 1 with 5, and then 6, no. So finally what you can do is that you can swap the value of the first element with the value of the fifth element. So here you will be able to get the value as 38, and here you will be able to get the value as 27. Now if you will see at pass number 2, what are the values that you will be able to get? You will be able to get the values as 19, followed by 27, followed by 45, followed by 79, followed by 50, followed by 38, followed by 29. So this is an array that you will be able to get after completion of your first pass, right? Now here if you will try to observe, at each and every pass, how many number of swaps I am doing. So if you will observe in selection sort, at every pass we are doing just a single swap. Once we are done with the iteration, we are saying that whatsoever be the final value of min we have, we are doing a swap with the first element that we have. That's it. And our task is done for a first pass. In the second pass also we did the same task. The only difference is that now we get rid of the one element. And we started with a 1 index and will reach until 6. And again, we did only one swap. Again, at the pass number 3, because we know that now the top 2 smallest elements we will be able to get in the selection sort, we can start with the element index at 2 until the element index at 6. Now again, the value of min, we can initialize it as 2. Again, it will see that is there any element which is less than 45? 3, no. 4, no. 5, yes. So we can just replace it with 5. 6, yes. The value 29 is even lesser than the value at 38. So it will be updated as 6. So now what we can do? We can simply try to again replace or do the swap between the value of the 2 and the value of the 6. So now what we will be able to get is 45 will be here and 29 will be here. Means after the pass number 3, when we are done with the third swap also, we will be able to get the value as 19, followed by 27, followed by 29, followed by 79, followed by 50, followed by 38, followed by 45. That is the thing that we will be able to get as a final result after the third pass. Now again, for the third pass, we can get rid of the 3 elements because we will be able to get the top 3 smallest elements in one go. Now, our focus is completely shifting towards the remaining last 4 elements that we are having, right? Now again, the value of min will become equals to 3. And now again, 79 is there, right? The next value is 50, which is less than the 79. So update the index value. Again 38, again we need to update. Again 45, no need to update, because at index 5 it contains the minimum element. Again we need to do the swap. So now 79 will become here, 38 will become here. Now again in pass number 4, what elements you will be able to get? You will be able to get the value as 19, followed by 27, followed by 29, followed by 38, followed by 50, followed by 79, followed by 45. And now because it's a pass number 4, means we get a collection of top 4 smallest elements. Means now our focus is just to work on these part. So here I am having an index 0, 1, 2, 3, 4, 5, 6 and 7. So in total we are having 7 elements. That's why the index will start from 0 and will go until 6. Now again we just need to focus on 50, 79 and 45. Again the value of min will become now 4. So it is 50. Next is 79. No need. 45. It's lesser than this index. So we can do a just replacement of that. And after that, because we are completely done with the array, we can do a swap. Swap with the first element, which is 4. So here 45 will be here and 50 will be here. So it means that after the pass number 5, we are having this kind of array: 19, 27, 29, 38, 45, 79 and 50. And here also top 5 elements are in already sorted fashion. Now we need to just take care of the last 2 elements. So here the value of min will become 5. We will move ahead. Now the value at array of 6 is somehow smaller than the value of array of 5. So we will replace the value with this. And now again a swap will be required. A swap will be required between the value of array of 5 and array of 6. So we will be able to get the value 50 as here and 79 will be here. So after iterating with the pass number 6, what we will be able to get as a final output: 19, 27, 29, 38, 45, 50 and 79. So this is a kind of a final sorted array that we will be able to get as an index number 0, 1, 2, 3, 4, 5 and 6. Here if you will see, this is nothing but is a sorted array. So here again if you will see, in worst case scenario, as we are having a 7 elements, we are keep on iterating until the n-1 number of passes, means 6 passes are required here, right? The very important point here to note is that how basically it is better as comparable to bubble sort. In bubble sort, it is trying to do the swap at each and every consecutive elements. But here it takes one smart move. What is that smart move? It says that I will take one variable whose name is min, whose basic responsibility is to take care of that index which contains the minimum value. And finally, at every pass, I will do just single swap, where I will just swap the first element of the array with the minimum value that we have. And at every pass, I will be able to get rid of that many elements. So I will take care of only the upcoming elements that I have, right? So for example, first pass, it will be able to get rid of this 19. Second pass, it will be able to get rid of 19 and 27. Third pass, it will be able to get rid of 19, 20, 27 and 29 and so on. So always remember, in selection sort, at every pass, we will be able to get the top smallest elements. First pass, first smallest. Second pass, second smallest. So 2 smallest elements. Third pass, 3 smallest elements. Fourth pass, 4 smallest elements you will be able to get, and the cycle keeps on moving. So basically here if you will see, the important point to note in the selection sort is that first important point here to understand is at every pass, just try to understand this point, only I would say one swap is required. At every pass, if you will observe, only one swap is required. So if I will say that you will be having, in worst case scenario, n minus 1 number of swaps, so n minus 1 number of passes. So what is happening is that, so at every pass, so suppose you are having n minus 1, at n minus 1th pass also you will be having the one swap until the very first pass also you will be requiring a one swap, right? So in total, what I am saying is that if I will talk about that how many in total number of swaps are required in a complete array, it will be nothing but is equals to n minus 1 swaps. So in worst case scenario, what is the time complexity required in case of a selection sort? It will be order of n. Whereas in a bubble sort, it was order of n square, right? It was order of n square. If I will talk about the number of comparisons, so here we had a talk with the number of swaps, and we have seen that whenever we are talking about number of swaps, somehow selection sort is performing way better as comparable to the bubble sort. Let's talk about the comparison, number of comparisons. Is the performance is better or not? So when we talk about number of comparisons, again at every pass we are getting rid of that many elements. First pass, one element deleted. Second pass, two elements we are able to just filter out. Third pass, three elements we are able to filter out, until so on when we are left with the only one element for the comparison. So here if you will see, it is again a sum of n natural numbers. Here we are having n minus 1, so it's a sum of n minus 1 natural numbers. So overall time complexity will be order of n square when you apply the formula of n minus 1 into n divided by 2 into n divided by 2. So here if you will see, the time complexity will be big O of n square. Time complexity will be big O of n square. So in a nutshell, what we have learned about the selection sort? The very first thing, selection sort always tries to give us the smallest element in every pass. Second important thing is that the logic, the way it works is that at each and every pass only the single swap is required, because here we are having a min kind of a variable which is basically responsible to contain the index of a minimum value, minimum element. After that, we have seen that the way its logic is working, the worst case scenario number of comparisons will be order of n square, number of comparisons when we are talking about, right? And when we are talking about the number of swaps, it will be equals to order of n. So these are the few intuitions behind the selection sort which I want to discuss in this particular session. What we will do in our upcoming session, we will try to discuss the implementation for the same so that you will be able to get a better understanding about this. But before going closing this particular session, can you tell me what is the time complexity requirement here? So here if you will see, again the time complexity will depend on the two factors. Here also when we are talking about the time complexity of a selection sort, so it simply depends on two factors. The very first factor is the number of comparisons and the second factor is the number of swaps. Now here when we are saying comparisons, it means that it is nothing but is equals to order of n square. When we are saying the number of swaps, it is nothing but is equals to order of n. So in a nutshell, what is the time complexity? It is nothing but is equals to order of n square, because we need to talk about big O. We need to talk about the worst case part. That's why the overall time complexity is order of n square. So far, I hope that you already have watched my previous session where I have talked about the logic behind the selection sort and how mainly that selection sort is different from the bubble sort that we have discussed in the previous part, right? Okay, so one thing we have understood that selection sort is somewhere smarter as comparable to bubble sort, in the sense that here it is tracking the minimum index by saying that the index which contains the minimum value, and for every pass it is just trying to do the one swap. Now, whatever be the logic behind that and whatsoever be the time complexity aspect for the same, I have already been covered up in my previous part. So I am not repeating that aspect again, but what I want to cover up in this session is the implementation for the same, so that you will be able to get the better understanding of the selection sort. So what I can do is that I'll try to open the Jupyter notebook here. I hope it's quite visible to everyone. Let me rename this file by saying the selection sort implementation. Okay. Now here what we can do is that we will try to take first of all the array. So here I am writing the driver code where I can take the array elements. So let me try to take the same array elements that we have here. So what are the elements that we have? We have 50, 38, 45, 79. So let me write this first. 50, 38, 75. Let me write some other numbers because again going back will take some time. 29. Here I am having 11. Then I am having suppose 17. Then I am having suppose 20. Then suppose I am having 37. Okay. This is the array that I have now. Now what I can do is that I will store my result inside this variable named result. And here I can call the function named as selection sort, which will basically take the array. Now what I can do is that I can print the values selection sort of the given array elements is. So here what we can do is that we can print the result. Now what we can do is that, so this is something which we called as a function calling. This is something which we called as a function calling. Now we need to define this particular method. So here comes the function definition. What we can do here is that we can define the function definition by saying selection sort, and inside that we can pass the array arr. Now what we did here is that we need to take one variable named as min index, something like that, which is basically responsible to take or store the index of a minimum element. So now here what we can do is that we can start with a for loop I in range, which will go until the value of the length of the array that we have. Or another thing that you can do is that we can simply store the value of the length of the array inside the n, and we can call that as n, right? Now here what we can do is that here we will say min index, which is basically responsible to store the index of a minimum element. So min index is basically responsible to store the index of the minimum element. Here if you will see what we can do, we can simply try to store the value of the I. Now here inside this we can call another for loop, which is basically used to traverse the elements starting from I plus 1 until the length of the array that we have. So what we can do is that we can say for j in range, it will start from I plus 1 and will go until the value of the n minus 1. Fine. Now here we can make one simple condition. If suppose the value of the r of j is lesser than the value which is present at the r of min idx, r of min index. So it means that there exists the element in an array whose value is lesser than the minimum index value. At that point of time, we need to update the value of min index, right? Min idx with the j index, because it means that that is the index which contains the minimum element as of now. And this is what we keep on moving. Once we will be able to completely traverse the complete iteration of the one pass, we will do the swap. We will do the swap of the elements at I and min underscore idx location. If you already have watched my previous session where I did each and everything or each and every iteration by using a blackboard, then you will be clearly able to understand the implementation also. So here if you will see, what I can do is that now one simple way to do the swap in Python is this. So here what we are saying is that just do the swap of these two positions that we have, right? Ar min index and the value of ar of I. And finally what we can do is that we can simply return the array. We can simply return the array that we have. That's it. So now here if we will try to see, are we getting the sorted array? When I run this code, 11, 17, 20, 29, 37, 38, 50 and 75. Which is pretty much awesome. Why? Because this is what we are expecting as an output. This is what we want, right? We want a sorted array. And how basically we sort this array? We sort this array using a selection sort. And here in selection sort, the major thing is to store this min index. And here after each and every pass, means after completion of each and every j starting from I plus 1 to n, we are doing a swap only one number of time, right? As you can see that here also we are using two for loops. So in worst case scenario, if I will talk about the time complexity of this particular code, so you can simply say that the time complexity to run this code is order of n square. So if you remember, when we are talking about the bubble sort, at that point of time also, we got the time complexity as big O of n square. And in this selection sort also, we are getting as order of n square. Then where is the difference? Difference lies in the fact, the way the logic it is working when we are talking about a bubble sort and when we are talking about a selection sort. Somehow in bubble sort, at every pass, we are getting the greater elements. In first pass, higher one. In second pass, top two bigger one. In third pass, top three higher one. Because they are storing at the extreme rights. In selection sort, we are getting the smaller elements at every pass. First pass, first smaller element. Second pass, top two smallest elements. Third pass, top three smallest elements. And so on. So basically, the way, the approach is completely different when we are talking about a bubble sort and when we are talking about a selection sort. And that's what you need to understand, okay? So I have showed you in both of the scenarios also what's the proper intuition behind that, followed by the implementation for the same. So in this particular video, we will try to see the logic behind the insertion sort, and with the help of which we will try to talk about the complexity analysis for the same, okay? So until so far, we have discussed that how basically selection sort will work, how basically bubble sort will work, and we have also talked about their implementations with their time complexity as well as the space complexity analysis part. Whenever we're talking about insertion sort, here it's like a deck of cards. When you used to play, how basically you used to display the cards, according to that only the sorting algorithm for the insertion sort will work. What do we mean by that? Let's try to understand the concept behind the same. So here if you will see on the blackboard, I have written some random numbers which is present inside the array. So the index of these numbers will be 0, 1, 2, 3, 4, 5, 6, 7 and 8. Now what will happen is that initially, suppose, so you are having the number 75. Obviously at the very initial instance, when you are having a single element, that element is already sorted. So you will not do any much work towards that, right? At 0th index. But the question came when the next element came into picture. So what basically this insertion sort will do, when this 90 will come into picture, it will try to just compare that element with the element before that. Means 90 will get compared with 75. As the value 75 is less than 90, it's in already a sorted fashion, so it will move ahead towards the next element. So basically what I'm saying is that first element already sorted. For example, I am having a card. In a card, I am having a number, suppose 4. And then the next card, the number is 5. So that 5 will be basically compared with that 4, and as the number 5 is more than 4, so I will place it towards the right side of 4, right? Similarly, here also what will happen is that step by step each and every element will be taken, and the element will be compared with the previous one at each and every instance. So now in the next pass, what will happen is that now 100 element is coming into picture, right? So we have 75, we have 90, and we have 100. Now this 100 is just compared with first of all 90. Again here if you will see, the value which is present as the upcoming as the front element is lesser than the 100. So it's fine. It's completely fine, right? 0, 1 and 2. And because it is fine, we will move towards the next iteration, which is having the element as 95. Now see this very much carefully. So here I am having 75, then 90, then 100. Now the element that we have is 95, right? Now this 95, which is present at third index, will again get compared with the element which is 100. Now here if you will see, the value 100 is greater than 95. Means at this point of time, a swap is required. So what will happen is that 100 will go here, 95 will go here. Now again this 95 will get compared with 90. Now here if you will see, this is completely fine. So basically what we are trying to do is that we are trying to see the new element with its previous index elements which are present. And finally we are doing a swap then and there, right? Now again in next part we are having 85. In the next part we are having element 85, right? So here our updated elements are 75, 90, 95 and 100, and now I am getting 85 at the index number 4. Now again here if you will try to see, we know that until this part our array is sorted. Now 85 is the new element that we have. So 85 will get compared with 100. So here if you will see, this 85 is less than 100. Or in other words, 100 is greater than 85. It will just compare with the previous element as well. It is also greater than this 85. It will again get compared with the previous element. Here if you will see, 90 is also greater than 85. Here if you will see, it will again get compared. 75 is less than that. It means that this particular element will be placed at this particular location, and all the elements will get moved towards the right side, right? So here this is the new data or new array that will be formed after applying a insertion sort. So basically we will be able to get 75 followed by 85, 90, 95 and 100, right? Now when next element will come, what will happen? Again the new element will be 50, right? So here we are having the elements as 75 followed by 85 followed by 90 followed by 95 followed by 100, right? The next element that we have will be having a value of 50. Now again the same thing will happen. This 50 will get first of all compared with 100. So it is 0, 1, 2, 3, 4 and 5. Now again the value 100 is greater than 50. So we are sure that we need to compare this 50 with the previous element as well. So if suppose in the very first iteration itself you are getting a value which is less than the element that you have, at that point of time you can completely say that okay, my position is fine because you are already having a sorted array. But given a situation like this where the previous element is greater than the upcoming element that you are having, so you need to compare until or unless you will not get that element whose value is less than this element, right? So again if you will see, 95 is also greater than 50. So you will go more back. 90 is also greater than 50. You will go more back. 85 is also greater than 50. You will go more back. 75 is also greater than 50. It means that this element should be placed at this location at 0th index. So all the elements will get shifted up front. So here it will be 75, 85, 90, 95 and 100. So how these things are done, that implementation is very easy. I will show you in the next part of the video. But here my major focus or my major intention is to show you that how basically insertion sort will work. What's the logic behind that? So here we are done with 75, 90, 100, 95, 85, 50. In the next part again we are getting 100. So here if you will see in the next part we are having, so again here we are having 50, we are having 75, we are having 85, we are having 90, 95, 100 and then again 100. Now here if you will see the elements are same. Elements are same, it means that this can be fine, right? The element should not be greater in the previous part. If it is greater, then we need to go back and do the comparisons. Now, moving ahead, we are having 110. So, when we are writing 110 here, so what will happen? 110 will again get compared with the previous element. Now here again, if you will see 100 is less than 110, completely fine. We can move ahead, right? And then we are getting the value as 7. So, in the next part, what will happen is that 7 will come. Now again, this 7 will get compared with the previous element that we have. Now again here if you will see 110 is greater than 7. So we will go back. 100 is also greater than 7. We'll go back. Comparison will happen. Again 100 is greater than 7. Again go back. 95 is greater than 7. Again go back. Until or unless I am getting the value which is greater than 7, I'll move back. So 90 is also greater than 7. Go back. 85 is also greater than 7. Go back. 75 is also greater than 7. Again go back. 50 is also greater than 7. So means what we are trying to do is that we need to place this value at the very starting location and all the elements will be shifted towards the right side. So 50, then we are having 75, then we are having 85, 90, 95, 100, 100 and 110. So finally, we will be able to get an elements which is 7 followed by 50, followed by 75, followed by 85, followed by we can say 90, followed by 95, followed by 100, followed by 100 and 110. So here if we will see, this is a kind of a sorted array that we will be able to get 0, 1, 2, 3, 4, 5, 6, 7 and 8. So in total we are having 9 elements which is of a sorted manner. So this is a sorted array that we will be able to get finally, right? With the help of a insertion sort. Now here if you will try to observe, if suppose you are having an array in an ascending order, already in an ascending order. So what will happen in that particular scenario? If you will try to observe, for example, I am having this kind of an array, 10, 20, 30, 40 and 50. If you will try to apply the same logic here, so initially you will be having 10, right? Then in the next part, 20 will come. Now here if you will see, when 20 will come, 20 will get compared with 10. And the value present before 20, which is 10, is less than 20. So it's completely fine. There is no swap which is required, right? We will move ahead. Now here if you will see, 30 will come. So 30 will get compared with 20. So again the value of 20 is less than 30. So there is no swap which is required. We will move ahead towards the next element. 40 will come. So now 40 will get compared with 30. Again the value which is present before 40, which is 30, is lesser. So no swap will be required. Nothing we need to done. So it's just that at each and every pass, what is happening is that we are making a comparison. we are making a comparison, that to a single comparison, and we will be able to reach to a solution that there is no as such swap is required, right? So here if you will see, finally I am having 50, right, in my array. So again this 50 will get compared with the previous element, which is 40, and 40 is less than 50. Again it is fine. So when I'm having 5 elements, I think I am having 5 elements here, right? 0, 1, 2, 3 and 4. So the number of elements are 5 here. So when I am having 5 elements and when I am applying a insertion sort in this particular case, here if you will see, I am doing just 4 comparisons. This is 1, 2, 3 and 4. At every pass, I am doing just single comparison, right? Initially, there is no comparison required, right? Because we are having a single element. So here there is no comparison. Here there is no comparison. And after that, 1, 2, 3 and 4. Means what I'm saying is that suppose if you are having n elements, in that particular case, when we are dealing with a ascending order, there is only n minus 1 number of comparisons which are required. And how many number of swaps are required in this case? So when the array is already in ascending order, we have seen that, okay, n minus 1 comparisons are there. That's completely fine. We have observed that. But are we doing any swap here? No. So there will be 0 swaps which are required. So in a way what I am saying is that for this particular case, 0 swaps are there. So whenever we are talking about a time complexity part, this is a kind of a best case scenario. This is a kind of a best case scenario, I would say. Best case scenario in an insertion sort, where I am saying that your array is already in a sorted fashion, or in a almost sorted fashion also. Insertion sort will give the best case scenario. Why? Here our time complexity depends on 2 factors, comparisons and the swaps. And here if you will see, it will be equals to order of n. Here it is 0 swaps. So overall the time complexity in an insertion sort will be equals to order of n when we are talking about an array which is in a ascending order, which is in a sorted fashion, and that too in an ascending order. So at that point of time, when we are doing an implementation of insertion sort, we are getting a time complexity as big O of n. Why is that so? I have clearly talked about. Now let's talk about the worst case scenario. What will happen when I am talking about a worst case scenario of the same? In case of worst case scenario, your array should be in a descending order. Descending order. What does that mean? For example, your array will look like 50, 40, 30, 20 and 10. And this is the indexes of your array that you have. Now here what will happen? Suppose initially you are having an element which is 50. So it is at index 0, no comparison. Now the next element will come 50 and then 40. Now here if you will see, 50 is greater than 40. So swap will be required. So 40 will come here and 50 will come here. This is 0, this is 1, right? Again, after getting 40 and 50, in the next part, we will be having 30. So now here if you will see, 50 is greater than 30 and then 40 is also greater than 30. So finally 30 will come here, 40 will come here and 50 will come here. So what I'm saying here is that at each and every time you will keep on doing the comparisons and you will keep on doing the swap when we are talking about a worst case scenario in an insertion sort. Again, if you will see here, the next element is 20. So when next element will come into picture, 30, 40, 50 and 20. So again there will be a comparison. Again there will be a comparison. Now there will be 3 comparisons if you will observe. Why? Because 50 is greater than 20, then it will move ahead 40 is also greater than 20, 30 is also greater than 20. And then again 3 times swaps are required, and we will be able to get this kind of an array. And finally, at the very last, if you will observe, when we will be having the element which is 10, so what will happen? 20 will be here, 30 will be here, 40 will be here, 50 will be here, and now 10 is coming into picture. So now this 10 will get compared with 50 first, right? 50 is greater than 10. Then 40 is also greater than 10. Then 30 is also greater than 10. And then 20 is also greater than 10, right? Now 4 comparisons, and after that 4 swaps are required in order to get a final result of a sorted array, right? So here, if you will try to observe the number of comparisons and number of swaps. Initially, 1 comparison, 1 swap. 2 comparisons, 2 swaps. 3 comparisons, 3 swaps, right? And 4 comparisons, 4 swaps. So here, if you will try to observe, when I'm having 5 elements, there will be 4 comparisons and 4 swaps. What I want to say here is that if you are having n elements in your array, you will be seeing that you will be having n minus 1 comparisons and n minus 1 swaps, right? When you are having n elements in your array. So if you will do the addition of all these number of comparisons and the number of swaps, so here if you will see, the number of comparisons will be the summation of all the elements that you have from 1 to n minus 1, right? And this is nothing but is a series of sum of n minus 1 natural numbers, which is equals to n minus 1 into n by 2, which is equals to order of n square, can I say? Similarly, number of swaps will be also equals to the same. It will be equals to 1 plus 2 plus 3 until the value of n minus 1. Again, can I say that this is equals to n minus 1 into n divided by 2, which is equals to big O of n square? So now here if you will see, the time complexity again in an insertion sort depends on the number of comparisons plus the number of swaps. Which is having a bigger value? Both are having a similar kind of complexity. So in worst case scenario, when your array is in descending order, the time complexity will be equals to big O of n square. That is the important takeaway from this session. So 3 things we have learned in this session. The very first part that you have understood is that how basically insertion sort will work. What's the logic building of this insertion sort? How basically this will work. So we have seen that this will work just like a deck of cards we used to play, where we need to see the upcoming element and then we need to compare that upcoming element with the previous elements that we have, and accordingly we need to do the comparisons and the swaps required. After seeing the logic behind that, we have seen that what is the worst and the best case scenario of this insertion sort. So we have reached to a point where we can say that best case scenario will happen in an insertion sort when an array is in a ascending order, or when the array is almost, I can say, sorted in a ascending order. At that point of time, we can say that the best case scenario will happen, which will give us the time complexity of big O of n. The worst case scenario will happen when we are having a time complexity of big O of n square, and that will happen when the array given is in a descending order. At that point of time, we will be able to get a time complexity as big O of n square. It's a very important interview question where they can ask from you that, okay, what is the sorting algorithm that you will use if your array is almost sorted in an ascending order. So what should be your answer? And they will obviously ask for the reason behind that. Your answer should be that I will go for the insertion sort out of the available sorting algorithms, because insertion sort will give me a best case time complexity as big O of n. Why is that so? I have completely demonstrated you. Here, when we are talking about a almost sorted array, in that particular case, the number of comparisons in total will be n minus 1, but there will be almost 0 swaps, and that's why cumulative, the time complexity will become big O of n. Whereas when we talk about descending order, at that point of time, cumulative, the number of comparisons and the number of swaps will be big O of n square, which makes the overall time complexity as big O of n square. So that is the overall idea behind the insertion sort, which I want to show you in this particular session. I hope that this part is pretty much clear to everyone. If you still have any sort of doubt, do let me know. I'll for sure try to resolve it as soon as possible. With this, I would like to end this particular session. In the next upcoming session, I will try to show you the implementation of the insertion sort. I hope that before coming to this video, you already have watched the concept related to the insertion sort, where I have talked about the logical understanding of insertion sort and how basically it will work. So if you remember, let me take one simple example. For example, here we are having an element which is 9, 5, 1, 4 and 3. So if you remember, basically what usually happens is that the first element will remain as it is, and then for the next upcoming element, we used to compare it with the element before that element. Meaning, what we can do is that we will take 2 pointers here. There is one pointer whose value will always start from 1 and will go until the end of the array. So for example, here we are having an index which is 0, 1, 2, 3 and 4. So it will start from 1 and will go until 4. So this is I. Then we will take some other pointer whose value will start from I minus 1. For example, in this case, it will be 0. So majorly, what is the logic behind insertion sort? Let me try to do the implementation side by side. So for example, here, if I will write the driver code, what we are saying is that, for example, here we are having an array which is 9, 5, what was the elements which I picked up here? 9, 5, 1, 4 and 3 suppose. 1, 4 and 3. Now, let me try to store it inside one result. And what we can do is that we can call the function. So there is a function calling here which is going on. And here we can form a insertion sort. Inside that we can pass the array. Now we can print the sorted array after applying the insertion sort is. Now here if you will see, we can print simply the result. Here we can define the function. So here comes a function definition. Here what we can do is that we can say def insertion sort, and here we can define the array. Now what we can do here is that we can simply we can make one for loop whose value I am saying that intentionally we will start from 1, because first element in an array which is having 0th index is already a sorted one. It will go until the length of the array that we have. Right? Now what we can do is that inside this we can store the element which is present at array of I inside the key. Meaning what I am saying is that this element which is 5, which is present at array of I am storing it inside one variable called as key. So 5 will be stored here, right? So here is the implementation of the insertion sort. So I'm trying to show you a driver code side by side. So here if you will see, key is equals to 5, right? Okay. Now what is the purpose of storing this key? I will show you. Now what we can do is that we can take the value of j as I minus 1. This thing is also done. So the value of j will become now 0. So when the value of I is equals to 1, So this is happen when the value of I is equals to 1. Key is equals to 5 and the second part j is equals to 0. Now there is one important condition which is completely responsible for the implementation of insertion sort. What is that? What I can do is that now I will make one while loop. I will check whether this value of j should be greater than or equal to 0. In our case, yes, it is. And second condition is that is the value of the key is less than the value of r of j. Suppose these are the two conditions which are very important to understand this part. Please take attention in this particular part. So here if you will see, yes, the very first condition says the value of j should be greater than or equal to 0. In our case, we having the value of j as 0, so this condition is satisfying. Second condition is saying that the key that you have, which is 5, the key that you have is having a value should be less than the value of r of j. So here if you will see, what is the value of the key? It is 5. Is that value is lesser than the 9? If yes, because here if you will see, this condition is also true in our case. If yes, what we want to do? What do you want? You want to place the value of r of j at r of j plus 1 position. This is what I want to do. I want to place the value of, so here I am having two values as of now, 9 and 5. So j is 0, I is 1. I want to place the value of r of j, which is 9, to the value of r of j plus 1. Meaning, I want to place this value of 9 at this position. So I did that. Now what I will do is that I will say decrement the value of j as j minus 1. So in this case, when the value of I is equals to 1, at that point of time, the value of j in our next iteration will become minus 1, because 0 minus 1 is minus 1. And whenever it will become minus 1, at that point of time, because we have applied the while loop, again this condition will get checked and this condition will become false, because now the value of j is not greater than or equal to 0. So it will go out of the while loop. And out of the while loop, what we can do is that we can say that just place the value of the key at r of j plus 1 position. So now here if you will see, I already have stored my data, which is 5 inside the key. So what I will do is that this 5 I will place at j plus 1 position. What is j? Minus 1. Minus 1 plus 1 is 0. So it means that I am saying at r of 0 means this position I will place the value of 5 here. And that's what I will do. So here if you will see, what I will do is that if this condition is satisfied, place the data of r of j to r of j plus 1 position, and after that decrement the value of j as j minus 1. Once you will be out of the while loop, do one thing for me, place the value of key at this position. And if you will repeat this task again and again for all the remaining upcoming elements, you will observe that you will get the final sorted array. Here we are getting none because I didn't return the array. So let me return the array, then you will see the magic here. Here if you will see now, you will be able to get a sorted array which is 1, 3, 4, 5 and 9, right? Let me show you one more time the same iteration. This is the thing which is happening. Now we will be able to get the value as 5 and 9, right? Done. After that, what is the next element? 5, 9. Now we will go to the next iteration. Next element is 1, right? So here we are having 0, here we are having 1, here we are having 2. Now in this iteration, the value of I will become 2. The next element we are moving. Okay. Now again what will happen? What is the value of the key? The value of the key will become 1. Perfect. Because at the r of 2, the value is 1. What is the value of j? It will be I minus 1. So the value of j will become 1. Now we are moving towards the while loop. While the value of j is greater than or equal to 0 and the value of the key should be lesser than the value of the r of j. These are the two conditions inside the while loop. Then only we are going. So here the value of j is 1. So it is true. After that, if you will see, what is the key? 1. Is the value of 1 is lesser than the value of r of 1? 9. Again, this condition is also true. So what we are doing here inside that? We are placing the value of r of j which is 9, to arr of j plus 1. So I am placing 9 here, right? This is the first step where we are saying that whatsoever be the value present at arr of j, place it at arr of j plus 1 and then decrement the value of j by minus 1. So here the value of j will get decremented to 0. Now again a certain check. J is greater than equal to 0? True. What is the value of the key? Key will remain same, 1. Is that less than the value of arr of j, which is 5? It's true. Again, I will place this value of arr of j to arr of j plus 1. So 5 will be placed here. Again, the value of j will get decremented to minus 1. Once it will become minus 1, it will go out of the while loop. And once it will go out of the while loop, what we are saying is that whatsoever be the value of key you have, place it at arr of j plus 1 position. What is the value present at arr of j plus 1? So minus 1 plus 1 is 0. So I am saying place this 1 at arr of 0. So finally we will be able to get a data which is equals to 1 followed by 5 followed by 9. This is 0, this is 1, this is 2. What is your task now? There are 2 remaining elements which are pending now. I did this, I did this. Now there is 4 for the value of I equals to 3. And then there is 3 at the value of I equals to 4. Try to do at your home. Try to apply the same logic which I just showed you. And in this way, I just dry run my code as well. The logic which I have written on the Jupyter notebook file, right? So here what you can do is that for the remaining 2 elements, first of all, try to dry run that and see whether you are getting a sorted array or not. And if yes, then easily you will be able to get that how basically this code is working, right? This is what the overall implementation of insertion sort. With this, happy learning to all. Bye bye everyone. See you soon in my next upcoming video.